Now, in Calc 3, one of the ways I like to approach Calc 3 is to tell you all the math you ever learned in your life before Calc 3 was two-dimensional math. And there are problems that are so much harder as a result. Calc 1, what is the most hated form of differentiation? It doesn't have a close second. You remember?
The quotient, the epsilon bit.
No, differentiation. Do you remember?
Oh, the limit form of it?
No.
Oh, implicit?
Implicit, okay, yeah, I knew I was going to get that eventually. Everybody hates implicit. It's so long and it's so involved. Then you get to Calc 3, and you learn a shortcut that's like, my God, this is so easy. Why didn't they show us this in Calc 1? Well, you have to know partial derivatives and stuff. The point being, and I maintain this all the time in Calc 3, if you look at the world, everything three-dimensional, and by the way, I'm going to give you an absolute mathematical statement. All the math you ever did in your life through the end of Calc 2, you can look at from 3 dimensions. It wouldn't change your answers, but it usually makes things easier. A circle is not a function, but a circle is a very important shape. How do I make a circle a function? I want to remind you of stuff that you really do know. Circular paraboloid. Slice it horizontally with the plane, and what is your cross section?
A circle.
A circle centered at the origin. All circles are cross sections of circular paraboloids. Circular paraboloid is a function in 3 dimensions, therefore derivatives, calculus, everything about that is actually quite easy. Everything about a circle, quite complicated. The reason implicit got so easy is because you stepped back and looked at it. Everything is a 3-dimensional problem where I'm just looking at a level curve, a cross section. And by the way, there's no exception. I can show you everything you've ever learned in your life is actually just simply a snapshot of something in 3D, a cross section, a level curve. And if I look at that from that point of view, everything is so much easier all of a sudden. A lot of the complication goes away. Everything, if you can draw it on a piece of paper, I don't care if it's a figure 8, it's not a function at all in 2 dimensions. But it is a slice of something that is a function in 3. And that was why it was so important. So those of you who were in my class, you got that message and then you started seeing things differently. We're doing math of one independent variable only in this class. But there are problems, like today, that if we step back and look at it from the Calc 3 lens, let's look at it as a 3-dimensional problem, and then we're just going to, well, how does this become 2-dimensional? Give me a positive real number. That's the height of your C, and now that's your R squared. It's actually that simple. So one of the problems that you did last semester was, do you remember doing independence of path? Remember those kind of problems? Where you say, you have the integral, right? You have the line integral from point A to point B, but if I could prove it was independent of path, I only had to look at the endpoints. That made it so much easier. Now, you did it 2 ways. You did it function of 2 variables, you did function of 3 variables. And so what we did was we said, let's suppose, hypothetically, there is an f of xy. I called it the grandfather function. When I take the partial derivative of this, which we just wrote like this, and then I take the partial derivative of y, which we just wrote like this, okay, and I put them inside of a vector. We'll do this version, not the third one, because the third one, then I need the curl and all that stuff. We're not going to go that far, okay? So now I'm calling this function, if you remember, f, and we said by definition f is what type of vector? Starts with big C.
A conservative.
Conservative, which is the most important kind. If I start with a function and I create the vector f by taking the partial derivatives of this, what's another name for this?
Gradient.
It's the gradient of little f. But we don't really need that. If I start with this is called a potential function. If I take the gradient of this potential function, I create a vector that is automatically conservative. If you just randomly made up a vector, would it be conservative? Probably not. Right? I actually have to reverse engineer it. If I just randomly made one up, I could do that the rest of my life and none of them would be conservative. I actually have to think it through. So I'm handing you a vector. And by the way, the notation we would use is, if you remember, This is a function of x and y, this is a function of x and y, we just call them n, and then if there was a third one, that was p. I'm giving you this, I'm not telling you this exists, and I'm asking you, is the vector conservative? Now, we're only going to do the two variable problem. The three variable problem, I need to do the curl, it's more work, and we're not going to do that problem. There's no way I can make that one, one independent. How did we check? Well, again, I'm starting with f.
If the
The partial derivatives match.
If I take the partial with respect to x, and then I take it with respect to y, or I do y and then with respect to x, aren't these always equal?
Yes.
Regardless of the order? Yes, that's an absolute all across the board. And I say this kind of jokingly because when I was a student, is f sub xy the same as f sub yx, because that indicates the order? And the teachers would say, well, they are the same as long as they're in an open interval surrounding the point you don't have, they throw all the conditions. And I was the student who asked, well, can you give me an example where it will ever fail? And the best answer I ever heard was, no, it can only fail in theory. There is actually no tangible example where it will ever fail, but we don't call it an identity. We don't say it's always true. We say in theory it could fail. It's just we have nothing to actually use, even theoretically, where it would fail. So we have to just say, suppose there was a function where it failed. But there isn't one, is kind of the net result. Therefore, it never mattered what order you did your partials. This is always true. If this came from little f, then what must be true? Does that ring a bell?
Yeah.
That's how I knew it was true. And if that statement was true, then what? Then I integrated either one of them going backwards. Again, this is what you did in Calc 3. So we said f of little xy was either this or it was this. You never did both. It wouldn't make any sense because you're going to get the same result. You don't do them both as check, don't you? You do one and you differentiate it. You did one or the other, and that's how you got back. Okay, does that ring a bell? Now, the difference is when I do the arbitrary constant, it's not a constant. What is it?
A function of y.
It's a function of the, let's say, the missing variable, because I could do either one. Remember when you had 3 variables? Then it was a function of 2 variables and so on. You did this in a vector sense. We're going to do the exact same mathematics, but in a differential equations environment. There's no vector associated with the problem, but we're still going to treat it trying to find the f of xy. Okay? So, let's suppose we have something of this form, and I'll be redundant, say it's this. We write it like this. I don't really need to write the of x and y, that's automatic. But you're saying, wait, but in the end we're going to have a one variable problem. You're right, in the very end we want it to be one variable. But that doesn't mean it has to be a function. For example, what if when you solved baby algebra, okay, Calc 1, I prefer to baby algebra at this point, you guys can see that. Is it possible we did everything, we solved our differential equation and it ends up being a circle? Sure, that's not a function, but it's still two-dimensional. When you get done, your answer doesn't have to be a function, it just has to be two-dimensional. So I get done with this problem at the very end and I find my f of x, y equals stuff with x's and y's all over the place. How do I make it two-dimensional? By now saying I'm going to pick a particular level curve. In other words, set it equal to a constant. What if this is x squared plus y squared? F of x, y equals x squared plus y squared. That is three-dimensional and it's a circular paraboloid. But it has to be a two-dimensional problem because I technically can only have one independent variable in the end. So now I just set it equal to c and now it's a circle on the xy plane. That's like the easiest step that exists. Okay? If you were given an initial condition, you would have a value. Don't even worry about initial conditions in these kind of problems. So what we're going to do is take a Calc 3 concept of how we found the answer. There's partials in this. So when I say there's no Calc 3 in DiffyQ, this is where we have a little bit of Calc 3 in DiffyQ because we're borrowing a trick that we could not answer this question otherwise, but by looking at it that way. Okay? So I'm starting, sorry, where is it? I'm starting with this equation here. I would love to be able to say f of xy is simply the integral of m dx or n dy, but I don't know if that's true. I'm going to start by taking the partial derivatives. If Then we say this particular equation is the word we use. I wasn't there, by the way, when they decided. We say it's an exact equation. So this will now be our third type of differential equation we're going to solve, an exact equation. And the solving of this is very different than the separable. It's very different than the first order linear we did last day. Okay, so let's see. I don't want to determine, I just want to solve. Let's see. All right, let's do one. Hold on. Okay, just making sure. All right. I'll do it this way here. As in any differential equation, it's not about the answer. It's about the process to find the answer. And if I get the process right, I'll always get the answer. So the first thing I'm going to do is determine if this is exact. By the way, do not make the blind assumption that every problem is going to be. They won't be. And if they're not exact, we may be able to do something later. Last day, we solved first order linear problems by finding that thing called an integrating factor. And then once we found that, we were able to proceed. Would it be mathematically possible that your integrating factor ends up being the number 1? The problem was so darn easy that you end up like, in other words, I didn't need one. I could have just gone with it. Yeah, it's not really going to happen. But every problem you deal with is not necessarily going to be exact. But if it's not exact, we're going to determine there may be an integrating factor that we're going to calculate that makes the new equation exact, and then we solve that one. That's a way more complicated problem. I think it's we will do it. It's lesser of a priority than this one, because this one is the much more common one. This is the Calc 3 approach. So this is my M, this is my N. So what is the partial of M with respect to X?
2.
Well, let's see, it's going to be 2x plus y times the derivative of that, which would be 1 with respect to X. What is the partial of N with respect to y? That's going to be 2x. I'm sorry. Hold on a second. With respect to x. I'm sorry. I said that wrong. Y x. My bad. I'm looking at that going, that's not right. Okay, sorry. Too close to the board. It's still this, by the way. And x is going to be 2y plus 2x. Are they the same?
Yes.
Mm-hmm.
They are the same. It is exact. That means that there exists a potential function, and I can solve it. And the solving, rarely is that going to be difficult.
So how would you state that answer? You would say the given differential is...
So you'd say, well, the question was, is this exact or is it not exact? This is exact.
So
That's why my check mark. Is this exact, yes or no? Yes, this is exact, which now means I have a very specific way of solving it. If it wasn't, I can't solve it, at least not yet.
Would the question be like, is this exact or is it not? And if it is not, fine, make the equation so that it is exact.
That is a possible problem. The problem with that is you cannot always find an integrating factor.
Okay.
You can often find an integrating factor, but it's like everything else in calculus. I'm trying to do a U sub, and in this case, the chain rule factor is not sitting around, and that's what it is. Okay, it wasn't sitting around, I need to do a different thing. I need to maybe do an integration by parts. You know, it's one of these things that the nature of this question is clearly not separable. We've got sums. First order linear, I think, is right out, it's just not going to work. Besides, I got, y to a power, it's not that either. So I'd say, well, the form that it's asked in, exact seems to be the most logical thing. Now, what if these were not equal? Well, I may be able to find an integrating factor, which we're going to determine today. But then the next thing we look at will be a form of differential equation that actually looks quite a bit different than this. One thing about classifying your differential equations when you guys do a lot of practice problems is they really start looking different enough that it's not that hard to classify them. Okay? And of course, there's always a handful of problems that can be done more than one way. Okay, there's always a lot of problems. It's really easy to set up a first order linear that ends up also being separable. That's not hard at all. Okay, so what I'm going to do is, now, when I teach Calc 3, I always do it the same way. I just integrate the first one. I never think about the second. And if there's 3 variables, or if there's a mn and a p, I don't do the last one. I just do the first one. Because you're going to end up integrating everything anyway. But I always do things, I do similar problems always in the same order. It's way more efficient. Then I don't have to think about it. So right off the bat, I'm going to say f of x, y is the integral of what? X plus y quantity squared dx. Now, when I integrate this, how do I treat the y? Again, this is the rare time you get to use a little calculator.
As a constant.
I treat it as a constant, so that really doesn't bother me. No, I don't need to do a u substitution because the chain rule factor is a 1. So I have things squared. So the antiderivative is going to be 1/3 thing cubed. Yeah, this is not complicated. I don't have any coefficients on the x. There's no exponents. This is it. A plus what?
Plus a function of y.
Plus a function of y. I'll call it g of y. If I, by the way, is it possible that that is a constant? Is it possible?
Yeah.
Absolutely. But is it possible there's actually a y, like a y cubed or a sine of y or e of y? Yeah. And if I don't do that, I won't be able to finish the problem. So again, I'm borrowing from your memory banks. Most of you did not have Calc 3 last semester, so this, yeah, maybe a little bit. Who had Calc 3 last semester? Well, then it won't be as hard to remember because you did this really late. You did this in December. How do I know? This is literally like 4th lecture from the end of the course. So it's, you know, it's a little fresher in your mind. You did that. This is the lecture right before Green's theorem, by the way. So it's that late in the semester. So now what I'm going to do is take the partial with respect to y. And what's the partial of this with respect to y?
With respect to
So it's going to be x plus y quantity squared
plus g prime.
plus g prime of y. Good. And if I did it right, what must that equal?
The
And
2
y.
That must equal
N.
n. Everybody good?
Mhm.
Now, I'm going to set this equal to that. Now, what might be useful? Yeah, it might be more useful I square that thing.
Yeah. Spread.
That's just not going to factor very well because the constant's not really helpful. You agree? So let's go ahead and multiply this out. If I square this, what will I get? X squared plus 2xy plus y squared plus g prime of y, and I'm setting that equal to 2xy plus x squared minus 1. Well, that makes it a little bit easier. I'm going to be lazy. Can you tell me what g prime of y is?
Negative 1 minus y squared.
Let me ask you a question. What if you got that?
Oh.
You did, but what if you got that? Okay. Anybody here work on a submarine or a ship or anything? No. You know, the flashing red light, you know, you're gonna go DEFCON 3 and all that. This would be, we made a major, oops, I don't wanna say screw up, let's say a major error. Yeah, it's impossible. Your function of y can't have any x's in it. This would be really bad. But my function of y isn't a constant, it's a function of y. Cool. So, what's g of y? Well, it's the integral of this dy, which is what?
It's,
Sorry, I
One-
just
one
have a
over-
quick question.
Yeah,
I'm
do
just
something.
answering this. But that first line that you said fy equals this x plus y squared plus g prime of y. How did we set that equal to 2xy?
Well, first of all, we're saying this is the answer, I just don't know what this is. But this is the answer once I figure out what this is.
Yeah.
But the partial of this with respect to x is this. The partial of this answer with respect to y is this.
Oh,
So I'm taking the partial of this with respect to y and then setting it equal to the end. That's exactly the same thing you did in Calc 3, you know, if you haven't had that recently. And by doing that, I can figure out what the g prime and therefore the g of y. So what's g of y?
Negative y minus 1/3 y cubed.
I'll call it C1. You do not get to choose a constant here. There's going to be a constant in the final answer. And the constant is not life and death, but it is a constant and it probably isn't 0. So now we're almost done. Now my f of x, y I can say is 1/3 x plus y cubed minus y minus 1/3 y cubed. Now, you can, it might not be a bad idea to cube that. I'm not saying you have to. Why might it not be a bad idea to cube it? Because there's going to be a 1/3 y cubed, and there's a minus 1/3 y cubed. They're going to cancel. Let's just be really lazy today. We'll leave it alone. But you all see that if I expand it, I'll actually get to cancel stuff. Plus C1. Am I done? Almost. Tell me why I'm not quite done yet. Tell me about that answer.
It's a 3-dimensional.
That answer is 3-dimensional. In other words, think of f of x, y as z if you want to. That answer is 3-dimensional. So what I want to do is then say, well, let's just set this equal to, I don't know, C2. Yes, it would be very useful to expand this, but for right now, I'm not worried about it. So if I throw that over, why don't we just call that result, I don't know, C. And there's my final answer. And that answer lives
In the
in 2
2-dimensional.
dimensions. That last step that I did is absolutely trivial, but it is important because I can't give you a 3-dimensional answer because we only have one independent variable. And by the way, there's no z in the problem, is there? There's only x and y. So I really can't write my final answer as z equals. But this is where we used, I said make it 3-dimensional in order to solve it and then come back. When you learned the shortcut for implicit, everybody loves that shortcut because, my God, it's so easy. It's because you took your 2-dimensional problem and looked at it as a slice of a 3-dimensional problem, solved that one, and then answered the question. And there was no loss of generality. What I do in my Calc 3 class, a lot of you were in there, I start by taking a Calc 1 implicit differentiation problem and we do it from beginning to end. And I don't always make the easiest ones. And then I'll take a Calc 3 implicit problem. I'll say I have this function and let's assume that g of x, y, exists, but we can't solve for it directly. And then we do implicit on 3 variables, and that is like the ugliest thing ever. Then I'll show you, I'll derive the formula for doing, remember, just negative fx, big F sub x over, like, I'm done in 10 seconds. And then I show you in 3 dimensions, it also works. Oh my God, this is so much better. Yeah, because we looked at the problem from a different point of view, and then forevermore, there's no more derivatives that are difficult to take. We had to do this. We said, let's look at this as a slice of a 3-dimensional problem. Therefore, our derivatives are partials. But now when I come back, my final answer here is absolutely 2-dimensional. But is it possible that my final answer is not actually a function of x? Is that possible? Yeah, in this case, because of the cube, it actually will be a function of x. Because I could actually, or I should say, oh, no, actually, I'm sorry. No. The y cubes are going to cancel, aren't they? So I'm going to have a y squared, aren't I?
Yeah.
So I can't technically write the final answer as a function of x. So that's more along the lines of a circle or something, except this would be way uglier than a circle. And I answered the question. I don't need to write it as a function of x. I just need to write it 2-dimensional.
Meaning that you're equaling it to the constant.
By saying, there's an infinite number of constants that would make this statement true. I'm just saying, I'm picking an arbitrary constant. Now, like the picture I drew earlier with the paraboloid, I'm doing a slice that automatically made it, the slice is 2-dimensional. So, this is 3-dimensional, But the moment I set it equal to a constant, I looked at one specific cross-section, one specific slice. I have a two-dimensional curve now. And in case that messes you up, when I did my paraboloid, I cut it off up in the air. But you guys remember this in Calc 3. You stand, where do you stand? Do you remember? Where do I always have you stand? On top of the z-axis. Come on, you remember that. I say stand on top of the z-axis, which is, look down and close one eye. And what do you see? You see a two-dimensional curve. Can you figure out how high off the ground it is? No, you just see a two-dimensional curve. So you see the circular cross-section of my paraboloid when you're standing on top of the z-axis and looking down. That is a two-dimensional curve. The fact that it's off the ground is irrelevant. It's still two-dimensional.
Now that example of the paraboloid that you drew, in fact, you can still kind of see it. We could have picked any level curve, but not the negatives. So is
Well,
that-
yeah, because this was above the end.
Right, and so does that ever come into play where the C, we have to pick a certain range for C?
No, but you're not picking a value for C, but you can say, will this be true for all real numbers C? And now I'm looking at this quantity right here. Now, if I expand this, I'm going to have an x cubed, I'm going to have an x squared y, I'm going to have an xy squared. I will have no y cubes, and then I'm going to have a minus y. And you look at that going, could this ever be negative? Yeah. Yeah, if y is large positive and x is small positive, yeah. And could this ever be huge positive? Yeah. Could this ever be zero? Yeah. So are there going to be, on this problem, are there going to be restrictions on this C, do you believe? I don't know if I can say yes or no absolutely. I would say probably not. What if there were? I think we only worry about it if it's obvious. I don't think it's worth your time to try to figure out if there are restrictions on the C. It's not that important right now.
So we just say
But it's a
that
good question.
C isn't just all real numbers on the real line.
Well, right now, I don't think there is any restriction, but you're saying this is the form of my answer. If I wrote the equation of a circle, if I wrote x squared plus y squared equals k, is that still a circle? Yeah, tell me about k. K is the square of the radius. Oh, but k certainly then couldn't be negative, could it? Because we're dealing with real valued functions. Could k be zero?
Yeah, but you.
It'd be boring, but that means it's 1 point. Is that wrong? Will that not work? Or will that still work? So we just say that in that case the k was non-negative. But we like to write it as r squared to remind ourselves. But do I actually have to? When I just did that parabola a moment ago, f of xy equals x squared plus y squared, just pick a random positive value for f of xy. Does it have to be a perfect square? Aren't all positive real numbers perfect squares? 3 is a perfect square? Yeah, it's root 3 squared. Pi is a perfect square? Yeah, it's root pi squared. Yeah, sorry, but we were going over this in Calc 2 today. I hate to say that all the math you've ever learned in your life, it's not all wrong. It just isn't all right. You haven't been lied to. That's what I always get asked. Have I been lied to my whole life? No, the truth has just been withheld. What you hold as absolute basic truths usually aren't. They're only true if it's purely real numbers. How many have had linear algebra? Did you do, I guess that should be everybody, did you do any complex vectors? Vectors of complex numbers?
I think literally.
I would hope that at the end of, in my course, that's what we do at the end, in chapter 8 of Larson. Most people don't get that far. So dot product changes, doesn't it?
Yeah.
The definition of dot product actually has to change because you can't get a right answer. The dot product we learned for real valued vectors is correct, but for complex it won't work. So you have to change it to conjugating the second term, which isn't important if there's no imaginary component, but it is, so in other words, we have to even change the definition of dot product. We have to change certain things to make it work always, and then we go back and look at the real numbers going, okay, it doesn't affect my real number answer. It's still gonna be valid, but I need it to always be true, not only sometimes be true. And we're gonna find that out all throughout this course, I hate to tell you. You're going to see things go, oh, that I have fun with this one. Every time you ever said no solution, that made perfect sense at the time. Every time in baby algebra you said this cannot be factored, it made sense. Both of those are lies from the pit of hell. There's no such thing as a no solution. There's no such thing as not factorable. Every polynomial is factorable.
Imaginary numbers.
See, the no solution was an incorrect answer. What was the correct answer? No real solution, which for what you were doing was just as good. I have a parabola that is completely above the x-axis. What are my x-intercepts? There aren't any in the real plane because they would be complex numbers. But does that mean I can't set it equal to 0? No, it just means I won't get a real solution. There's no problem with that. We're okay with that. Everything can be factored. It just doesn't necessarily have to have integer coefficients. You were told always that you can't solve an unfactorable equation. You know, x squared minus 9, I can factor that, therefore I can set that equal to 0. X squared plus 9, obviously you can't, it's a difference of squares. X is plus or minus 3i. Okay, but x squared minus 7, you can't do because 7 is, you know, it's not a perfect square. Well, wouldn't plus or minus root 7 be the answer? Of course I can factor it. You can factor everything. Fundamental theorem of algebra, which you should have learned in pre-calculus, you actually go through. And when you set any nth degree polynomial equal to 0, you get exactly n solutions. Some may be repeated, some may be complex, and the complex solutions generally come in conjugate pairs if your coefficients are real. Not true if they're not real. But you have all these absolute rules. You go, ooh, oh yeah, that kind of, everything else not really true if I simply go by that, which is how you did all your calculus stuff. So a lot of the stuff we learned, like, don't take it with a grain of salt, but be suspicious. Use a lot of side eyes, right? Like, wait a minute, they said that, but it's not really.
Oh, I do that all the time.
In this class, the answer to every question has got to involve one independent variable. That is the nature of this class. You're maybe going to take a class where that's not the case. I feel bad. I did that class in like 3 weeks or 4 weeks of an intersession once in college. Didn't truly enjoy it. I was bald at the end of that session because my hair was on fire, you know, the usual. PDEs is not fun, but it is necessary if you're going to be an engineer. I'm a math person, so that really wasn't necessary. But I understand things. Don't remember the problems. It was, like I was telling somebody yesterday, it was a few presidents ago. Like a lot of presidents ago.
For instead of integrating MDX to find fxy, we can do like MDY.
Yes, and it will be the exact same number of steps, and you're going to get the same answer. But what's the difference at this stage of the game? You'd have function of x here, and then you do the partials the other way. You all know this from Calc 3, so I can give you just a horrible, horrible problem, and I say I want you to find, you know, the cross partial fxy, and you're going, I have the nastiest function in the history of the world, but it's purely a function of x, and then I'm adding y. Why don't I do the partial with respect to y first, and then with respect to x? Do you remember doing that in Calc 3? Hopefully you did that in my class. You actually have a choice. It never matters. It's not going to change the answer, but there's an easier route when I'm doing derivatives. But it turns out in this sense, there's not an easy route. It's going to be the exact same amount of work. In the long run, you're going to do the same stuff. So you just do one or the other. Don't do them both and try to equate them. That actually won't work. And I have people do that in Calc 3 all the time. They try to do them both, equate them. They get two arbitrary constants that they try to equate and get magically functions of x and y with constants. No, don't. Just do one. Okay, let's do another before we move on to the other part. Make sure we have time. Hold on. My eyes are not working properly.
Well, that's a good textbook.
Say again?
That's a good textbook.
Yes, the print is just a little bit small for me. Hold on, I can see that this.
My favorite textbook.
Okay. I'm straining to see this is so. My eyes are just not working like they used to. Okay. Y squared cos x, we might as well throw something triggish in there. Minus 3x squared y minus 2x dx plus 2y sine x minus x cubed plus log y dy, and that's all equal to 0. It has to be equal to 0 because if it were not equal to 0, it can't be equal to a constant or even a function because it would still have to be a dx or a dy in there. And here's the reason. Could you, if you wanted to, write this as a first, well, okay, not first order, but could you write this as a first order differential equation, not first order linear? Could I write dy dx and get it isolated? Sure. Could I write dx dy and get it isolated? Yes. So if you decided to write dy dx, then you'd have this thing dy dx plus this function equals 0. What if this is not 0? Then what happens when I do the dy dx? what do I have over here? It's neither dx nor dy, nor dy dx nor dx. It's impossible. Yeah, I can't do this problem with something else in there because of the form. Okay? You with me on that? So there's no trick questions.
So we would always expect homogeneous function. or
Homogeneous.
equation. Okay.
Different word, different spelling.
Oh my God.
I'm glad you brought that. What does homogeneous have to do with in this context?
It equals zero.
The zero. What is homogeneous?
Of a substance?
That means you all look the same.
Yeah.
Homogeneous means you're undetectable. It's not a math word, it's an English word.
And they're spelled differently too.
Yeah.
Oh my God.
Homogeneous is E-O-U-S, homogeneous is just O-U-S. They're spelled differently and pronounced differently. It's good to know that. What do you do with milk?
Homogenized.
You homogenize it. What does that do? Mixes it all up so the cream doesn't separate from the milk. That's what homogenization is. If you are, I say this laughingly, none of you guys would ever do this, but if you were to join a fraternity, literally the definition of a fraternity is a homogeneous group of people. Homogeneous, bunch of zeros. No, a homogeneous group of people. It's a group of people that are literally the same in every way. That's why they band together as a fraternity. That actually is the whole point of fraternity. A bunch of people with like-mindedness and everything about them. And even, it's funny, they all look the same at some point. No, I'm not joking. That is, look it up. That was always the whole point. So it's a homogeneous equation. I cannot do this if it isn't. We will be doing things, and that actually has come up. The first order linears you solved, those weren't homogeneous, were they? You had functions on the other side. No problem with that. But the separable, no, you couldn't have the dx dy and then a constant on the other side or something on the other side. That no work. So this is my m. So what is my? Hopefully I did this correctly. I want to make sure I didn't write that in correctly.
2y cosine of x plus minus 3x squared.
Minus 3x squared. What is nx? 2y cos x minus 3x. I like it when I can do this. Is that a good thing? Yes, a really good thing. This makes my life so much easier. And as long as what I'm about to integrate isn't complicated, there's no integration by parts, there's no techniques, I should be done with this problem relatively soon. It's when they're not equal that we have more work in front of us. It's not impossible. It's just we can't do it yet. Yeah.
Yeah, so it's just not gonna be, if they're not equal, it's not exact.
It's not exact yet. There is a possibility we can make it exact. And that's all I can say is a possibility. I cannot guarantee. Think like basic integration in Calc 1. For every integral you could integrate, you could tweak it. And I did this last day in my Calc 2. I said there are a lot more integrals that you cannot do than those you can. And at first they kind of looked puzzled. We can all do this. Agreed? Hopefully. On my,
I thought that was the one we're supposed to skip.
yeah, that's what my Calc 1 students did, yeah. Now tell me about this one, in general.
Into the f
Usually,
of x divided by
Well,
f of x prime.
if f of x is 3x, well, f of x is a non-linear anything. Put anything in there for f of x. Cos x, log x, x cubed. Guess what? Few exceptions, you usually can't do this one. Aren't there an infinite number of f of x's like what there? And there are very few that you can do, like you can count on one hand. You take something you can do, you tweak it slightly, all of a sudden you can't do it. So what do we learn? Things like Taylor series and all those to deal with that kind of stuff. We learned other ways of doing what's called asymptotic convergence, powerful forms of estimation. That's not what we're doing here. Here it's a little more black and white. We can either do this or we can't. If we can't, there might be an integrating factor. If there is, then we can do it. If there's no integrating factor, then we
Yes, we can.
can't using this technique. You learned how to do U substitution in Calc 1, and then you get to Calc 2 and you say, but my chain rule factor's not there. I can't use U substitution, therefore I can't do the problem. No, you just can't do the problem using U substitution. There may be a different one. I might not, let's say that wasn't exact. Then I can't do it this way, but what if it turned out that it ended up being separable? What if it turned out that was first order linear? Okay, it's not exact, I would use a different technique. And every problem you're going to run into in this course, I guarantee you, you will be able to solve using some technique. But you won't be able to solve every problem using every technique. in this section, and this is what I like about the homework, every problem in this section is similar. And somebody asked me this last day, they said, can I try problems, can I try different techniques on the problems? Yes, but why? You want to get good at this technique now, and then when you learn the next technique, get good so that you are really solid. Then when you look at a problem, you go, this one I can do 2 different ways. Great. But most of the time, you probably can't.
So first you want us to find if it's exact and then find the solution to that equation.
Yeah, that's what we're working on right now.
And then I must have missed this, but what does it mean for something to be exact? Like,
For it to be exact, it means that these partial derivatives are equal, which means there was a potential function that existed where this is the partial with respect to x, and this is the partial with respect to y. It's basically the terms of the gradient of the force vector that you got when you took, right? That's the calculus, but we're not doing it from a vector point of view. But we're still doing the same calculus in terms of the integrating and differentiating. That part didn't change. There's no vector associated with the problem, but if you think about it, when you did path independence and stuff, you integrated something. You didn't use a vector at that point. Remember, you were doing an integral, lest you forget. You don't need to remember this exactly. This is what you did in Calc 3. And I gave you, x1, y1 to x2, y2. If this was path independent, all you had to do was find the potential function, and the answer was then f of x, y, evaluated from x1, y1 to x2, y2. This is what you did then. Do you see a vector in this question? There's one there. You know what the vector is. The vector is, and we proved that earlier. We proved that that's what the vector is because we do the dot product, we do all that stuff. But when you're actually performing this problem, you never actually do anything with a vector. You just know the m and n came from the vector. So we're doing something very, very similar right now. We still have the m dx and the n dy, and we're still integrating to find our f of x, y. Ah, okay. Difference is, what is the answer to this question? Do you remember? No, I'm looking for one word. Starts with a W, ends with an irk. Work, good. Yeah. I knew it would come to you guys eventually. The answer to this question is work. It isn't anything else. It can't be anything else. So it was a very specific problem. Oh, because I'm talking about a variable force along a path. How much work did I get done? Okay, that was the whole point. We're backing up. We're saying we're just solving a differential equation. We're not applying units to it. But could it represent work also?
Yes.
Yeah.
So this method just uses the relationship of the partial derivatives, fx, y,
Yeah.
like that, to solve it.
We're pretending that there is that grandfather function, I call it the potential function. We're pretending it's there because that's 3-dimensional, getting an answer and then slicing our answer to make it 2-dimensional again. It's not cheating, no. It's being clever. It's being very clever. It's what you did in Calc 3 to do implicit differentiation. You pretended it was 3-dimensional when it wasn't, and thought of your answer as a slice, which made all parts of that problem a lot easier. There's nothing wrong with making it easier. All right, so what's the answer?
Y squared sin x.
All right, I'm gonna give you guys a minute. You tell me, I tell you everything. I try not to tell you anything, but it happens. Okay? I'm gonna just ask you, so, what is this, the first iteration?
Y squared.
Sine of x
Y squared sine x.
minus x cubed y minus x squared.
Don't you love it when they put coefficients that
Yeah.
kind of make it no fractions? I laughed when I saw that.
Plus
Plus
some function of y.
some function of y. This part I want to be comfortable. This is differential equations. Are you supposed to know all the calculus you ever learned in your entire life up to? Yeah. Are you going to use everything? No. You're going to use the stuff that's common. What did I say were the big four? Remember?
Sine, cosine, exponential, log.
Well, exponential and polynomial.
Ah.
Log will come up, but actually a lot less common. And when it does come up, we're not worried. Polynomial-ish things. What do you have in this right now? Well, you have sine and polynomial. I mean, it's just, you see the same things over and over again. Obscure is obscure for a reason, because you just don't see it. What you have to do is you have to know where to find things. And I say this in all seriousness. When you guys are engineers and you're out in the field, you will know the things you work with and you will know them well. But the things that are obscure that you don't work with a lot, there's no reason you would know that. You will know where to find them. You're never going to guess. You will know where to find things. But the things you know, you need to know well, because those are the things you use all of the time. Okay? When you go to the same place often, do you go back and look up your directions every time you go? No, because you know it. But there's a place you haven't been to in a really long time. Maybe you look it up. A place you've never been to in your life. Probably should look it up. But after you do it a few times, do you still have to look it up?
No.
Did you memorize it? No. You learned it through repetition. That's how you learn most mathematics. So there really is a hierarchy. When I say the big four over and over and over again, at the end of this course, you're going to look back and say, my God, that was 99% of the problems. Now think about Calc 3. Pretty close to the same thing? About 99% of the problems? But you did the same kind of stuff. You knew where the more obscure ones were, but you did the same stuff all the time. All right, so Fy is, Fy is
2y sine of x minus x cubed. That's g prime of y.
this is not a partial derivative, is it?
Mm-mm.
If I'm in the three-dimensional x, y, and z, this I might have a partial at this point, but this is just a regular ordinary derivative. That makes my notation so much easier. Don't write a partial here, because it's a function of one variable. Now, I set this equal to
Your fy.
2y sine, that's good, or 2y sine, yeah.
Minus
This is looking good so far.
haha.
So far, so good?
Mm-hmm.
So what have I got at this point?
G prime of y equals 1.
Now,
It's ln of y.
interestingly enough today, in my, did I write? Oh, sorry. In my Calc 2 class today, interestingly enough, this was the first problem we did. We started integration by parts last day, and we did all the easy ones, x e to the x, and today we did all the crazy ones, x inverse tan x. We actually did log x using integration by parts. Wait a minute, how do you do integration by parts on the log function? Don't you need two functions? Yeah. The second one is a 1. And so the antiderivative of this, I believe, ended up being, if I remember
Y
correctly,
times
y log y minus y, I think is what it ends up being.
Yes.
I'm just going to tell you that. Could you do this using integration by parts? Yeah, and actually, if you remember, you're probably talking 30 seconds. It's actually really, really fast. This is not one I want you to worry about, because that's not an antiderivative formula. You know, that was a technique. And I said, occasionally you got to do a parts. Here's one of those. Okay, so I got this plus C1. Now, I'm going to be really lazy. Can you fast forward to the final answer?
Y squared sine x minus x cubed y minus x squared
So that's I can't see it.
y natural log y minus y equals c.
Plus y ln y equals C1,
C.
different C. What did we do before? Plus C2 equals C1, throw it on the other side. Did I ever write the f of xy? No. Did I lose anything?
Minus y.
Did I?
It's a y squared and it's also minus
Oh,
1.
hold on. I can't see the board. So it's this minus this minus this plus y log y, oh, there should be a minus y,
And
right?
it's also y squared sin x
It's y,
squared.
y squared sin x, thank you. I'm the only one that can't see it. Plus, equals c. Now, I don't want to check this because we kind of checked it in order to find it. It wouldn't have worked if we'd made a mistake earlier, would it? Everything worked out, it canceled beautifully. Okay, y'all with me on that? That's the solution. Is that two-dimensional? Yes. Is it a function in the xy plane, either of x or of y? No, because you see an x squared and you see a y
There's
squared.
a
No.
ln and a sine.
So what does it look like? I don't think of something absolutely ridiculously evil. I always start evil with like a figure 8. That's like the lowest level of pure evil. It's probably something uglier than that. And that's fine. That's the answer. So far so good? Yeah. Now, let's go back and let's pretend that something is not exact. Now, I'm gonna go through this slowly because there's two formulas that we're gonna develop. And the book does a good job explaining, but there's some shortcuts. And in any higher level book, they'll take lots of shortcuts there because they know you all can all fill in the blanks. I had a calculus class, it was actually Calc 1, back in the day. And I remember that class, it was 8 in the morning, 5 days a week. 1 hour, 5 days a week. And I didn't live near the campus, and so a couple days a week I'd stay with my grandparents and then go back home, and it was like 45 minutes away. I lived in the Santa Cruz area, and I was going to San Jose State. And I'm from that area, but I had to go over the mountains every day. It wasn't a fun commute. 8 in the morning, and all I remember about the instructor, besides the fact he was terrible, he was bald, and he sweat a lot. And the lights were really hot above his head. And all I can remember was his head glowed like a light bulb. And I would sometimes get lost in just staring at him because he glowed. It was almost like a halo effect. He glowed. And according to him, he was the smartest human being probably that ever lived. So we'd be doing calculus problems. He'd write the problem on the board. We'd write the answer. Go, any questions? And I'd usually be the one going, yeah, I have no idea how I got that answer. So he'd go through the problem, and I don't exaggerate when I said every problem he ever went through after we questioned him, he got a completely different answer, which means that every problem, this is 16 weeks of 5 days a week, every problem he ever put on, he did it wrong. Every problem. We're talking hundreds and hundreds. He would do every problem. It'd be like me giving you this answer without doing anything in between and being wrong. And he'd say, any questions? Every day I'd be like, yeah, can you show us how you got that? And of course, because we're working out, we're all getting something else, and most of us are getting the right answer every single day, and he's getting something else, and he'd never show us the steps or show us how he did it. Well, you don't really learn calculus that way. It'd be like saying, here's the problem, any questions? Good, let's move on. So, I want to walk you through the process. Let me go, I'm going to use the notation that the author's using for the most part, because it is what we're doing already. So I'm going to go back to this. mxy dx plus n of xy dy equals 0, and let's assume the existence of an integrating factor. But we're going to cheat it first, okay? We're going to cheat it first, and we're going to pretend that our integrating factor mu is a function of x and y for the purposes of being able to set up an equation. In the end, mu is not going to be a function of x and y. In the end, mu is going to be a function of x or y. But we set it up this way so we can get a series of equations. We're going to get two different equations. One, if it ends up being a function of x, if it ends up being a function of y. And you're going to see you don't choose. It falls into your lap which one it's going to end up being. Okay? So let's start by multiplying everything by that. And so I'll just write it this way. Mu m dx plus mu n dy equals 0. Now let's assume there is a grandfather function. Let's assume now there is an f of xy that exists. We have to assume there's a solution so we have a forward path. Depending on the problem given, there may not be a solution. You will know because you will run into an absolute dead end that cannot be continued, or it will be seamless and smooth. So what I want to do is take the partial with respect to y of this whole thing. I want to take the partial with respect to x of this whole thing. Remember, I'm saying pretend like there's a new thing now. If you want to call this, call this capital A and capital B, and let's look at those cross partials. Okay? So the partial with respect to y of this, product rule? Yeah, because it's a product of two functions. So first times derivative of the second plus the second times the derivative of the first. This is with respect to y. And I need to do this with respect to x. So now it's first times derivative of second plus second times derivative of first. And what do I need to do with these?
Set them equal.
I need to set them equal. Again, we're assuming the existence of the mu. Make sure I know this
Just a
correctly.
quick question, I guess.
Yep.
So like when we take these little derivatives, left is the y and right is the x. That's probably because like we're supposed to be using dx on the left, and so therefore we're going to derive it in terms of y. Is that
How
right?
did we get to here? This was the partial with respect to x, and so that's why we do it with respect to y, because we're getting the cross partials equal.
Yeah, so we have to like switch those.
Well, no, not they switch them. Let's assume this was exact for a moment. Forget all this. I'm taking the partial of this with respect to y because that's now fxy. I'm taking the partial of this with respect to x because now that's also fxy. And those will only be equal if this exists. So I said, let's start this problem by assuming that these guys' cross partials are not equal, but there exists an integrating factor, call it mu. So now that these cross partials, so now this is the partial of this with respect to x. This is the partial of this with respect to y, so now I'm doing the cross partials down here. Does that make more sense if you look at it that way?
Was it setting the partial derivative of x, the thing you're talking about, how like it just falls into your lap? Which one you're gonna say equal?
Well, that we don't know yet. We will look at what's in front of us, and I'll give you a hint. If what's in front of you ends up being purely a function of x or purely a function of y, it'll tell you which route you're gonna go. There are problems out there where it actually will work both ways. That's few and far between. So I have this now. So what I want to do, make sure I wrote all this correctly. I want to group terms now. Hold on. Got that guy. Okay, I want to put the mu's together. I gotta make sure I wrote this correctly. So let's just do it like this. And that one that way. I think, hold on. I'm going to do it the same order that the author's doing. I think the author actually did it the other way around. The author sent this one packing and sent this one packing. I want to write it in the same order because there's a clear set of formulas. It doesn't matter what order I do it, but my formula will look things reversed. And that's really confusing. I do it one way, the author does it another way, we're both getting the same answers, and you're going, which way should I do it? Okay, by the way, does it matter which way I move them? No. Not at all. Okay, so if I rewrite this, then on the left I'm going to have m mu y plus n mu x equal to this minus this, but I can factor the mu out of that statement. And that would be nx minus my. Okay.
How did you get
Did I lose something?
plus?
Why is it plus n?
Plus n.
Shouldn't be. What should it be?
The plus
Which
n.
way did I go?
It should be
Sorry, I
minus.
did mu my and I subtracted, thank you. That should be a minus. We're trying to find mu. So at some point you say, yeah, I'm going to divide by all this, but not yet. So now what we're going to do is say, what if? Okay, let's go the what if out there. What if mu really is purely a function of, and now we're going to look at two cases. This is where we want to be. So this is a what if question. Remember I said all we're assuming is that it exists, not what it is. So suppose mu actually is mu of x. There is no y in mu. It almost sounds like there is no I in team. Right? You know that's not true, right? You ever seen it? Oh, I can draw you the picture. I'll do that one later, but yeah. Okay, you wanna see it? You guys all know that one, there's no I in
Yeah.
team.
It's in the A.
See if I did this right. I saw this once, I don't have that, it's right here. I digress, but you know, Kobe Bryant's death was actually a significant event in my family. It was huge. So I watched his memorial. I don't know how many times I've seen it. Did anybody ever see that Shaquille O'Neal speech?
Yeah.
It's awesome. He told Kobe there's no I in team, and Kobe said, yeah, but there's an M and an E in that, you know. I won't repeat what he. I love that line. There's an M and an E. There's no I, but. Okay, if I suppose mu equals, sorry, we got really off track. There's something that's a zero up here.
Mm-hmm.
What's a zero?
The mu of y.
There's no mu of y.
Mm-hmm.
Now, I need this to happen because I have too much stuff going on up here. Does everybody follow that? If mu equals mu of x, then this is zero. That term doesn't exist because there's no y in there. So that's why I said start it with it being a function of two variables so we could get it set up, and then I'll make it a function of one. So what does that actually leave us with then?
Negative n mx.
So what are we trying to find, by the way?
Mu.
We're trying to find mu. So this is gone. I need to find mu, and I have these guys. Do I need to put them together more or less?